and there is direct to the water. The main purpose of this rainwater tank system. Next is the start of quality of improvement. How can we improve the quality of star water? That is the main, uh, main issue here. Next is the flood control. How can you control the flood? After that, landscape and how can you see the you are just giving the landscape, how can you see the beauty or means by seeing that, how can you see the that one. Next is the healthy living environment. So, living is from that how we are being the health point of view, that is the also main point. And after that, statistical layout of the rainwater tank system. This is the from the roof that to test the water rainwater and after to test the tank and from the tank uh, we can use for the toilet washing machine and toilet purpose. That is the here name out. This is the uh, tank can be kept here and the water is stored in that tank. And after that, you can use the water for the uh, means irrigator means so that water can be through the 5 year you can use for the lawn and other purpose here. Then here the background and purpose of this rainwater tank is that the rainwater tank being implemented under the IUW and oblique WSUB approach to address the pressure on traditional water sources. And here we can encourage the raising of event scheme and building codes here. It means that we have to give the concession so that encourage the people to use this, they can use the tank, their houses, so that they can store the water and they can benefit for the other purpose here. Next is the reduce the demand on main water. Uh, so whatever the main water supply from the municipality are coming to the different houses, that water can be used by to use this rainwater tank here. Provide the water source gardening during the restriction. If the water supply not coming from the municipality or main supply, then you can use this stored water in the tank for the irrigation gardening purpose. Reduce the peak star runoff and reducing the load of nutrients. The mostly having stored at the household scale is for the non-potable application. So mostly in house is a house hold scale means different remote area wherever the houses are there that they can use this and what was the water used stored in the tank not potable means not for drinking purpose except the drinking purpose you can use for the other purpose that the main here applications.
This water will be used irrigation purpose.
No, gardening purpose. Okay. Gardening or other purpose here in the houses surrounding. Okay. Uh, other things will be explained by sir.
I will be happy to talk.
Okay.
Answer your question.
Household rainwater tank is limitations. Only suited to household in separate dwellings arrangements with the sufficient roof area for the capture and space for the storage. So it depends upon the what is the area of the roof surface and how we are capturing the rainwater. Trends in urban normal stated city are for the increasing plot density, medium to high density developments. Okay. Uh, mostly used in the Australia and household not always maintaining and operating the system appropriate increasing failure rates. The maintenance is also a main problem here. Once you arrange the water tank to store the water, so you need the maintenance also. Or next is the water quality issue. Okay, so we will check the water quality also here. Provide mosquito breeding grounds, and we have to see the breeding of the mosquito. We have to avoid that one. Need to explore different configurations that may address the limitation in certain urban context here. These are some issues that can be kept in mind during the use of this household rainwater tank system in the uh, the key aspect of the data uptake of the rainwater tank system, that is the estimate rainwater system in and rainwater saving how much water collected the volume of water and water saving understanding that is associated with rainwater quality. What is the quality of water that is also a risk. Okay, they were able to check guidelines for managing the risk of rainwater use. So what were the guidelines of the rainwater managing the rainwater is there? We have to follow that one. Evaluating the cost effectiveness of rainwater tanks. After that, at the end of the slide, you can see the how can you calculate the cost of the rainwater tank. Understanding the inherent cost and benefits of rainwater tank, that is the one thing. Impact of rainwater system on star, water flow and nutrient loads here. The nutrient loads means once you are using long purpose, I think nitrogen, phosphorus, that is the main component of the water here. Impact of rainwater tank system on centralized water system and water quality. Once you are keeping under control this can use here. Energy consumption in the rainwater tank system. So building this one can use the energy here. The same the research topic of this rainwater tank here regarding that one. The main is the harvesting potential. How much quantity of water you are going to store the water, harvested water through the rainwater. System installation. We need the installation of the aspects of the regarding the rainwater tank here. Optimal design energy. Okay, and economics. Economics also playing the main role. How much money you need to do these things. Other things in the water quality also main issue and social issue and operation and management. These all things are required in the using the rainwater for the this purpose here. The other things are having the each component having the different issues and after that survey is there in detail here. Okay, just
Thank you.
okay.
What was your question?
How can you use for irrigation?
So, when we talk about irrigation for garden water, means the size of the rainwater tank is not sufficient to do the irrigation for larger areas. In this case, what we're talking about in the allotment scale, we have house and we have garden in the front and in the back. So these rainwater tanks which we are talking about, they're mainly about providing water supply for irrigation of the garden. Okay, so we don't need a very high quality water for irrigation purpose. So without any treatment, this is a non-potable application. Potable is for drinking purposes, drinking and single bit. So these are the three applications within an allotment or house where we need a good quality. For other purposes, like for example, toilet flushing, sometimes even for washing the clothes, and also for water, for car wash. We don't need very high quality water. Okay? The roof water which we are collecting, that can be sufficient, good enough for these purposes. So this slide which we're talking about, basically there is a potential for conducting further research in different areas. I'm talking about the areas with geographical areas. Like for example, in Australia we have done a lot of work in all those areas, looking the harvesting potential means with the roof area, the size of the rainwater, how much water you can collect, and then the rainfall pattern. So these are some of the aspects which we are, and how much we are putting demand every day on the rainwater. So yesterday, Professor Yar talked about that IS code. Okay, so and then he talked about that is a very good document. But I would like to say one more thing when you are looking those documents. He talked about that for 20 square meter roof area, and if the rainfall is 800 millimeter, the code gives me something around 64 meter cube per year.
Yes.
Is that right?
Yes.
So how this was derived? So basically, 100 multiplied by that is meter cube. And then you multiply by a coefficient or a factor, 0.8. Why we have to multiply that? Because we can't capture the 100%. That is 0.8. Again, that will depend upon the configuration of the rainwater tank system. Okay. So, the reason for applying this factor, when there is a, if you see a simple example of and then we have a rainwater tank over here, which is connected from the roof. So the gutters, which we are connecting these gutters, not from here, but we are connecting from gutters, okay? Down pipes. You have seen all the down pipes. So those gutters are designed either carrying 120 air. So they are not designed to capture all the rainfall which is on a heavy intensity. So that means all that rainfall, there will be some portion of that during some period when the rainfall is more than 120, that will be overflowing from the gutter. That's one factor. So the gutter is, so some portion will overflow. That's one factor. The second factor is wind. Okay? When the water is, so there will be some portion that will not be captured on that roof area. So that's another factor. Okay? The third factor that we provide first flush device. Okay? So initially some millimeter, this can be 0.25, 0.5 millimeter. Initial rainfall, we are not collecting it because the quality of that water is not. So that is another factor. Okay? Then there can be some evaporation. All those factors, they combine close to 0.2. Yeah. So that's why we are putting 0.8, but it can be up to depending upon the location, depending upon the nature of the system, it can be reduced to some extent, but in general it is 0.8. to estimate. That's one thing. The another thing which we have to keep in mind is that the calculation for the capacity of the rainwater tank. So what we discussed yesterday was that we will see how many days there is no rainfall. Is that right? So yesterday, I think it was 112 days or something, if I'm right. Yeah. So we consider that 112 days there won't be any rainfall. Then there are 4 persons in a house, and then we are providing how much water for each? 150?
135.
100. So that will give you the size of the tank. Yes. So now, what we have to keep in mind is that the number of days which were looked at 112, that will be independent of the rainfall. It will depend upon, because each and every geographical area, the overall rainfall can be quite high, but the number of days when it is raining can be significantly. Suppose we are in an area where we have 200 days. Okay? So I think what we calculated yesterday was around 58 or 56.
60,000.
60? 60 meter cube capacity. 1 meter cube, we also call it in kiloliters. Okay? But if you do this calculation by 200, it will be much more. It will be much more than 16.
108.
108. And how much water is available? Only 64 meter cube. So our limiting factor is 64. Okay. So you have to keep in mind that aspect too. That even if you provide 100, it's not going to work because the water is not available. Okay. So that because you have to take in your estimation. This is one aspect. But what I'm going to talk about today is using those 2 software I'm talking about. Use those software because they are doing calculation on each and every day. How much water is coming in every day, whether there is 0 or there is some rainfall, and based on that, there is water entering into the tank. And on the same note, there is a demand. Okay? And then you are also taking into consideration the evaporation loss in the wind. Again, applying the same value. Those values can be slightly different. So what I will suggest to you, I will go through a little bit more on modeling aspect, but use a very simple single half.
Sir, what about the flat roofs? What you showed that was especially
Okay, yeah,
because in India, most of the houses in plain regions, they have flat roofs.
yeah. So it doesn't matter much. The flat roof, again, there will be some losses. And that's why you have to have some historical data on the monitoring.
So the evaporation loss will be more, storage retention also.
Yeah. So you have to keep that in that aspect because over here, most of the groups they have very slight slope. Okay. Important to get it. But over in our part of the world mostly. So maybe losses can be slightly more in that case, but overall, and also over here, the gutters, we don't have gutters, we have some sort of opening over here in the ground point.
And people put filter in that question.
Yes, yes. So the losses can be slightly less. And that, for that, you need some sort of a monitoring and to get that factor. Okay, overcome. you need some whatever monitoring for a few houses and see how much actually the rainfall is captured. So in that case, whether it should be 0.8 factor or it should be 0.8.
Gutters are not required.
Yeah.
Because-
Where there are gutters? Yes. Then in that case, some factors, some issues will not be there in collection of rainwater.
When we are calculating the volume, we are more focusing about the dry spell, means how much dry period is there. Why so, sir?
But I'm not, that's why I'm moving away from that. What I'm saying is not dry for calculating the volume. Let's adopt another way of doing it. Every day, you see how much is the rainfall and how much the demand. Okay? When there is a rainfall, see what factors will be there to collect how much water is coming in based on the factors which you have considered. Okay? So you're not looking the dry days. What you're looking the whole year, how much water has been coming in and how much water is being used. So there will be days when there is no rainwater available in the tank. So you are doing actual calculations based on the availability of water in the tank. And then this size of the rainwater tank, we can start, say for example, for 10 kiloliters, then increase to 13, 14, 15. Run the model again. So at some point, what you will see that you will realize that with the increase in the tank size, we are getting more water because the demand is the same every day. Makes sense?
So one more question, sorry to interrupt.
Sure.
Can we combine tank for stormwater and rainwater? Is it possible?
So then why we need, that means we are allowing water to come on the, to hit the ground and then we are collecting. If you are making a combined tank,
Through the pipe,
Yeah.
filters, and then the pipe directly moves that rainwater to the storage tank, which is connected to the stormwater delivery. Is it possible?
so then you are determining the volume, deteriorating the volume. Water. Yeah. You are increasing the volume,
Yeah.
but you are deteriorating the volume. So I will.
Maybe then some rainwater treatment, that then the combined volume is increasing.
So how much cost you may be incurring for that option? That is another question which we have to address. Okay? Because when you are collecting rainwater just from the roof, then the quality can be considered much better than
Stormwater.
stormwater. Okay. So one thing, the other question which we're talking about, that, so this is the tank size. And that is the volume that has been utilized. Okay. So maybe when we start with 5 kiloliter tank, we may be getting that much amount of volume that is being that is available for application. When we have 10 kiloliter, so maybe that we will have a curve like this in general. So this gives you basically volumetric reliability. How much water is there is a demand? How much is the demand? And how much water is available? So that means as we increase the size of the rainwater tank, there will be more water available. Okay? But still there will be shortage of water. Because it may not be able to meet the 100% demand. So as I said yesterday, the volumetric reliability is the amount of water which is available and the total demand. So the demand will remain the same for the whole year, because we say for non-potable applications out of 135, if you talk about which is the total demand, say for example, 50% or 60% of that is for non-potable applications. That demand is constant. But with the increase of the size of the tank, the availability of water will increase. Okay? Otherwise, what will happen is all that water from the roof will be coming to the rainwater tank, but there will be overflow from the tanks. Because at some point, the rainfall is very significantly high, the demand is small, okay? And that means at that particular event, there is a lot of water, which will be overflow. Okay? But as you increase the size of the rainwater tank, that amount of water overflow the tank will be starting with. So in that case, maybe the situation will be that you need a very large rainwater tank based on the rainfall pattern. Say for example, take another example that you are in an area where the rainfall every month is very significant. And that is a very important aspect for rainwater tank systems design. In the areas where the rainfall is quite uniform, that means almost every month you are getting the similar amount of water. But you may be in a geographical area, and this is month, and rainfall in millimeters. So in January, maybe very high, then all the 12 months, there is a significant variation. So during those months when the rainfall is very low, the water is not available for sufficient water is not available for supply. So in that case, what options you have? Either you provide a very large amount of tank which will capture all that water. So it is a question of tank design. Inflow and outflow, what we call mass balance. Have you heard about masses? So you use the mass balance aspect, and that will give you the size of the rainwater. So to capture 100%, maybe you need a significant amount of large rainwater. At some point, with a large increase in the volume, there will be a slight increase in the volume which is available for application or use. So in that case, what we need to decide as engineers, at what point we should select a rainwater tank size based on that volumetric reliability which we talk about. And this factor, when we're talking about yesterday, number of days where the rainwater is not available. So the number of days can be significantly high if the variability every month of the rainfall is significant. So as I said, if you have 200 days instead of 112 days, then you need a very large size, but the water is not available. So we have to keep in mind while designing these systems about the actual availability of water. Is it making some sense or clear? Yeah. This is another thing which I want to add to what Professor Yadav discussed yesterday. It was a very informative and very good discussion presentation by him. But this thing came to your mind, which so using.
Actually, I think that depending on the rainfall, in many areas, when we are talking about household rainwater harvesting, if you actually try to calculate the way it was shown yesterday, the exact size would be abnormally very large.
The size?
Abnormally large.
Yes.
Abnormally large, and actually we are not able to accommodate in plot also.
Yes.
Because if for example, take small plots and the side setbacks are very small. So you will not be able to locate the tank itself.
Yeah.
Otherwise, like water tanks, you have to construct the
Yeah.
tank as a staging and then you have to house.
Yeah.
And I think if you what you showed just now, maybe if you can do something like a water balance calculation based on some taking some time step. That may help to work out that the volume you get can be sometimes much smaller than what we are trying. For the pattern that you showed, for example, every month you take what is the rainfall, what is the demand like that. Because as far as I understand now, most of the rainwater harvesting systems that these people are propagating in India, they are trying to supply only 20 liters per capita. They will just be consumptive use in the house, cooking and all that. They are not harvesting for the bathing and other.
So my response to that is that I'm talking about daily water balance, not even monthly water balance. We are using the climate data on a daily basis. Even there are softwares which can use 6-minute model. You're looking at every 6-minute demand and supply. Okay? But what we have estimated is that it doesn't matter much. The difference is not that big if you're doing 6-minute or daily. The daily estimation is equally good. So I'm talking about using those software I'm talking about on a daily basis. Even if you can develop your own Excel sheet, it's not a big rocket science. You can develop your own Excel sheet, and then you can have a rainfall for a couple of years, because you don't rely on 1 year rainfall data. You should look 5 to 10 years rainfall data. I'm also providing you and sharing with you 10-year climate data for Malcolm. And you can have a similar, and it's in the daily rainfall and temperature. Okay? And evaporation. These are the 3 parameters that we need. Okay? So you can also get the data from your meteorological institutions for that particular location, because then you'll be having rain gauges in different locations.
For data, temperature data we can get, but evaporometer is not, data is not available at many locations.
Yeah, so in that case,
You have to.
you have to play with the DCs in your area and all those things. So sometimes you really are not getting for each and every location. But I think there is one side, I'm not sure whether they can provide the data for Indian location, but in Australia there is one agency, they have developed software that you can give the coordinate for each and any location in Australia. They can provide you the evaporation, rainfall and temperature data.
That is for a graded data.
Yes, so it will be based on, so what they will do, they will see which are the closer 3 climate stations, okay? And they will manipulate mathematically, and they will provide you the climate data for any location.
Graded data.
Yeah.
I have a doubt also. So they will when to design a overhead sample. For the capacity, we plot supply curve and demand curve. And we see that there are the maximum two difference. Cumulating on the add, and we say that this is the.
We did the capacity.
Can you adopt the same approach here also?
We can, but in this case, it is slightly different, because you can very well on this. Yes, you can do that similar ways, and then what will happen is at few that can be done based on the diagonal pattern. Normally, we use that for using the diagonal pattern. How much is the variation in demand during the day? Okay, and the supply is constant. It is slightly different. So I will give you the example. So normally, this is how the diagonal pattern works. Okay, 24 hours, starting from 0 to 2. Okay. And then if it is a pumping or you are getting water from somewhere, okay? It can be a 24-hour supply from the source, okay? Then it is coming on an average demand, average supply. Yeah? Then you do the same water balance analysis by looking the cumulative effect. And then you're looking two things, maximum and minimum difference, and there is some that, okay? But that will not work over there because the supply is not constant. You are talking only about 24 hours over here. But over there, we're talking about the whole year. Okay, so the concept is slightly different. Yeah. This is the simple approach because you're talking about the dynamic demand pattern and then your supply, whether it is constant or not. Because if it is the pumping for only, say for example, this is your pumping for 12 hours or 30 hours, your that curve will mass curve will change in. Yeah, because the input is only for limited hours. Then the deficit and the magnetic value will be quite different. So the capacity will be significantly different. So what I was talking about was that so with using different size of rainwater tank, what you can do, what you will be getting is that each and every for different sizes, so for example, 5, 10, 15, 20, 25. The volumetric reliability, that is the ratio between what is available and what is the demand will be different. It will be significantly low, then it will increase in slightly. It will, so you will have a curve like this. And trying to run that model which I have discussed with you, what you do is simply take a single house, okay? Don't have to do much. Take a single house. Say for example, this is 500 square meter house. And then you see this is my roof area. Okay? There are 4 persons living in this house, and the total demand something I'm just assuming 75 liters per day for non-portable application. I'm talking about. Okay? In that model, you will be given the roof area, connected roof area to the water system. Your roof area can be large, but you have not connected to 100%. Okay? All that simple data has to go into that model. It is a very simple model. Okay? Then what you do is you start with 5 kiloliter rainwater tank and go in increasing. Then you will find different volumetric reliability. What you will see that at 10 kiloliter, you will be getting 80% reliability or 90% reliability. To get close to 99 or 100, you need a 50 kiloliters. Okay. So whether it is required to have a 50 kiloliters, and I think and you raise the very important critical aspect that whether you have the land area or not, you put a 50 kiloliters. Damage, the damage. If you are going underground, no. Partly underground, above ground, then whether how much is the cost efficient? All those factors has to be taken into consideration. If you see this sentence over here, what is changing in now slowly we are going to the smaller houses. Okay, slowly trend is towards increasing in density and reducing the allotment sizes. So what size we can fit in properly in the area which we have. considering the cost aspect. So all those factors has to be looked into while you are designing the rainwater system. So what I would suggest again, try to run a simple house using that software, and that software is capable to give you the stormwater flow, how much wastewater will be generated, how much potable water is needed, how much the alternative water source is needed, which is rainwater in this case. But you can have multiple alternative sources. You can also say that for toilet flushing, I'm using grey water system. So all those calculations can be done by simply changing the options. And the same process can be done for multiple houses. Yeah, we discussed yesterday, as I said. And we will provide a copy of that software. But otherwise, you can log in that website and you can download. Any question now? So, when we're talking about the slide, which was about looking. So these are some of the aspects to have a better implementation of rainwater management policies or increasing the adaptation of rainwater management systems, that we should encourage that how much actually potential you can get from rainwater system. So you need some sort of a calculation that highest score is already there. That can simply give you based on the rainfall and also the area how much it's accurate. But there is one factor which has to be taken into consideration, the variation in the rainfall pattern, which is not included carefully in the top. This is my, I've not seen that, but this is what I'm getting. Then how we can improve the water quality? Like for having the first flush, the screens and all those, that inform me. The guidelines, how to design the rainwater system. There are so many guidelines already available. It is just a question of collecting some information and using that under Indian conditions and developing guidelines. The social is basically the acceptance by the community. How you can encourage so that they have a feel of that it is their own system. Like for example, looking after their cars or other appliances or everything. So they have to keep it ongoing they have to do some maintenance. Whether we can train the manpower, there are plumbers available who can come and repair it. So the capacity is also essential if you are promoting those type of systems. Economics, then you think what is the cost we are paying for potable water supply which you are using for non-potable application. That is one aspect. The another aspect is whether by saving the amount of water, what is the cost externalities are associated with that? The environmental cost associated. Okay, you are taking a less amount of water. They are highly treating the water we are using for purposes where we don't need that quality of water. So the cost of treatment is significantly high. Okay. So that's why the cost of the water which is coming as potable supply is maybe expensive, but if you're using for different internal purposes, then you may need pumping. So in India, maybe that we can work out in such a way or system that we don't need a pump. So you can see a small pump there. Because it creates the pressure. But can we design the system where you can raise it up and put on some sort of a flap or a stand or depending upon the capacity, so that structurally it is strong. And there is one example which you can see over here. Basically, it is on a raised platform, but it is only being used for garden water. Okay. Where the flow is, the elevation is sufficient to create some gravitational force to flow that water. Okay. Any questions so far before I? Okay, so this book is already provided to you, and it has chapter 2, which talks about a lot of the modeling aspect of rainwater. So this is a copy is already being provided, and I showed you yesterday where you can download it free. Okay. So this is about general concept of rainwater time model. So you can see the precipitation, the initial losses, as we talked about, precipitation, evaporation, the area, there can be some, the first flush device, the water entering into the system, the storage capacity, and VT is the volume that is entering into a particular time. It can be on a daily basis. And then the water going down. And this is the dry volume where all the sedimentation will be deposited. And then you can clean it periodically. Okay, so that's why this gap. The outflow is slightly above the bottom of the tank. And you can periodically clean it, remove the sedimentation from here.
So in this case, it doesn't require a filter or something.
In this case, the filter is needed. So first, what type of filter you mean? Filtration before sending it to the home. So you mean filtration?
Get into the tank.
Get into the tank. You have first flush device, and then you can also have a leaf collection, a small screen on the top where the water is entering. Okay. So there is basically a screen, like example we have at homes, simple, what you call, chulli? Yeah. Chulli? Yeah. So we have a similar sort of we can have a strainer, okay? Simple mechanism. But if you're using this water for potable supply too, I think I will give you an example for 50 homes in a few slides, where they have a system only using collected rainwater for drinking purposes. So we have a treatment system for that. Okay, so you can read the modeling aspect is basically initial rainfall over time T, which can be 1 day, but there are models available that have, this modeling can be done on a 6-minute basis or even on hourly basis, depending upon the rainfall data which is available. But then you have to break your demand at the same interval. Okay. Then the initial losses, which can be the losses because of initial losses can be a little bit from the evaporation losses. Initial losses can be the first flush, which is being used, or some losses can be from the overflow of the gutter. Okay. All those things can be considered. Similarly, the continuous percentage loss will be the water being splashed out or blown out of the roof or gutters. Okay. Because of the wind area. IT is being flowed into the tank, reaching the volume of water in the tank at the end of the current time step. So after each day, there is a water coming in. So it is not actually coming at the end of the day. It is coming whenever the rainfall is the day. But because we have rainfall data for based on the each day on a daily basis. So there are 2 types of models which are available, where they are considering that the demand is before the water coming in or after the water coming in. Okay? So there are two possibilities which can happen. When we are conducting the modeling on a daily basis, there can be two options for us as a modeler. We are considering, okay, all the water during the day which we are estimating based on the rainfall pattern, but it is entering before the demand is taken off from the tank, or water has come in, and then the water is going out. So there are two possibilities. And in this book, which you will have in copy, both options have been taken into account. And there is, you will see the slight difference about the overall modeling aspect. Okay. But both are there, but there is not much of it. Which those who are interested to know a little bit more, they can go through the chapters, a little bit more on detail, but these are the two options which can be taken into consideration. So that will be total volume which is coming in is equal to the volume which came in A step before, then inflow to the tank, and this will give the total volume. Okay? What is the overflow? And once the tank is full, then it will calculate its it is recording that information as a variable, that what is the level of the water in the tank. And then it will automatically calculate whether there is an overflow, whether it is zero, or there is some quantity is flowed. So these are the benefits of using those software, which will give you a better outcome. And they will give you a little bit more better estimation of the rainwater capacity which you look based on those aspects which can be daily rainfall pattern, the demand, and the size. Then you have an option to select whether you want to provide a tank with a 90%, the reliability means the 90% of the time the water is available from the rainwater, or 90% of the demand is available from the rainwater. And this software will also give you the information that over that year, which days the water is not available. Okay? From that particular day, it will give you the information because you're using historical data. Okay? We don't predict, we use historical data for the last 10, 15 years. So I think the software can handle 10, 15, 20 years data, but 10-year estimation is good enough for any calculation. Right. So you can also write your own software. It is not a rocket science. Okay? Very simple approach. And you can use that type of model information and you can write your own software. Right?
Excel sheet.
So Excel sheets. Yeah. Or those who are modeling so software writing knowledge of different languages, they can use it. But even Excel sheet has Visual Basic in it, which you can use it. Okay. So as I said before, we should know how much energy is being there in the system, where we are providing pump. So what we did was that we did some lab experiments where we estimated that how much water, how much energy is required for providing services, water to washing machine, toilets, and dishwasher. So we estimated the amount of energy which is required by using different type of pumps. That is another study or research can be conducted from Indian conditions. based on the pumps which are commercially available pumps, that how much energy will be required if we are supplying water to internal applications. Either we do it by the gravitational way or otherwise, depending upon where the tank is situated. If it is underground, you don't have any other option other than providing it. So we did some work on based on that, and you can see there is a one complete chapter about giving all that information about the energy and usage and rainwater system. So this is what we plotted it out based on the different sizes, based on using different washing machines, collecting water, and we can estimate it based on the flow rate. The flow rate is high, the energy consumption is low, but these appliances, they need certain amount of flow rate. The intake is, even if you provide a pump of a high flow rate, it is not going to work because these appliances will take only a limited amount of water and water. Okay? So you have to trade off between what flow rate will be most suitable for your appliance. Okay? So that type of study was done to see using different flow rate pumps, AGC, and then all that detail is available in the book and you can read it. How the experiment was set up, how many times we estimated, and what was the size of the pumps which we used. So in India, there can be different efficiency pumps. You can consider doing some lab work. It is all about hydraulic assessment. Energy and water interaction is very important aspect. So the second part of my presentation will be on looking at the communal or clustering skills. So far we talked about individual, but there can be options where we would like to have a single rainwater tank for a number of houses. So what we do in those cases, as you can see over here, we're collecting water from each and every home and putting in a communal rainwater tank. And then, depending upon whether we're using only for potable application or non-potable applications, or for both, we will have the treatment options too. So I will talk about the treatment aspect and give you one example where actually this communal rainwater tank is being used for 50 homes. So you have two pipe networks. One is the collection, and for collection you have to have some sort of you have to provide a slope to the pipe. Okay. But the distribution will be in by pump because you need some minimal pressure. Good morning. It's going to be good evening very shortly, but thank you for that. So, in these type of systems, the advantage is that one, it can be managed and operate easily in comparison to individual tanks. You can better manage the water quality for all the, because everything is in the same line in one location. You can see the efficiency or the working of the treatment plant. So it can be better managed. You can be ensured better about the quality of water which is in the water. That is one advantage. Then the second advantage can be, if you think about it, there is a one rainwater tank system which is 5 kilowatt in one house. There are 50 homes. They each have individual rainwater tanks of the same capacity. But the population living in those homes is different. So the person one was single occupancy, the home will be using less amount of water. So by combining the capacity of rainwater tanks, you can increase the availability of water to the community. Yeah.
We have this system for portable water supply in our campus.
We have, I will give you an example where we have that system for potable supply.
In our campus also.
Your campus too? Okay. So you are collecting water from,
Municipal and then through pipe or there's a large tank.
yeah,
And from there it is distributed to each and every.
for houses. Okay, good. That
I
will,
mean, I would like to combine rainwater within that communal tank system.
okay. We can talk about that too, how that is possible, what implication that will have. Okay. So this is how the communal rainwater tanks can be designed.
But sir, how can use for rural area and rural areas? Like East India.
So in Australia, the rural house, which normally the houses where there are big individual houses in rural areas, they are dependent on their rainwater tank systems. And they treat it and use it for portable and non-portable applications. But at few locations, they also have the groundwater to top up in case there is a shortage of water.
We have rural house in Australia also.
Yes, we have. Yeah. And there is no piped water supply there because of the economics of scale. So no one can supply kilometers.
Sir, flood is very difficult.
Flooding is a different aspect. We can talk that separately. But let's talk about water supply. So this is how the systems are normally designed. So we have dual water pipe network. One is for collection, which is by gravity. And in case the topography is almost flat, so you can't have a system for a bigger number of houses, because the depth of the gravity system will start increasing. Okay, then you need to lift that water. Okay, that the energy involved can be significantly high. Okay, and there it is called the economics of scale. How large the systems can be, which is economical. And I will cover that aspect, that how we have done that calculation, which may be suited to a particular location, a particular system, but similar calculations can be done using the same approach, same methodology in any part of it. Yeah. So, the benefits of communal rainwater is opportunity for district to extend use of harvested water for fit for purpose. Basically, what you can do. This is very much suitable for remote community where they have 10, 15 homes.
We have maybe 20 houses.
You have 20 houses? Yeah. So these type of systems are suitable, okay, for remote community. And cluster systems are more suitable for high density developments. So where we have number of houses all together, these type of system will also be suitable because the land availability for individual homes, and if it is a multi-story, then you can't put the rainwater tanks for individual apartments. Anyhow, it has to be put on the ground. Potential economies of scale for infrastructure cost, storage, tank pumps, etc. should be considered. Okay. Opportunities for improved management compared to the house level scale I talked about that. improve yield and reliability of storage. Yeah, in comparison to single homes, because all that inflow will be combined together, the outflow is combined together, someone is using less water, someone is using more water, then you can meet their requirement. Topography is very important factor. Okay? Where there is a flat topography, the number of houses of which you can have a cluster scale of communal, the number can be smaller. But if you have a topography or slope, and then depending upon how you design your system, and that is something which we'll be talking about. Okay. So where there is a availability of slope, that means you need to have your collection system at the right center. So the cost of collection can be minimized. That's the want to have a gravitational force can be minimized. But there will be additional cost to the so that you have to see the trade-off economics here. So as you can see over here, when we have number of houses and the pipe is collection pipe is at its slope, then what we need is a sump valve first where the water which you are collecting from the roof that has to go to the sump valve. From there it will be lifted, and then it goes to the rainwater tank storage tank, and then it can be treated. And then drinking water can be stored separately and then pumped again to supply water. We need some sort of a system if you are using for potable supply. If you are not using for potable supply, then water quality will be sufficient enough. You can drink, you don't need that whole infrastructure. Yes. So you can see over here how the water is collected from the gutters. So this is the development in close to Brisbane area, which is the retirement rate of 50 homes. And this is the name is Capo di Monte, I think it is a French-based name. In this development, there are 50 homes, and you can see all those 50 homes that are supplying water to a communal storage tank. Those two tanks, they have a capacity of 200 milliliter each, and also close to that there is a borehole pump, tube well we call it over here. Because of the variation rainfall pattern, there can be a particular year where the water needs additional supply from outside. And this development is far away from any pipe system. Okay? So what they are doing is not only collecting the roof water, but they are also collecting all that wastewater. And close to that over here, there is a sump well where all that wastewater is coming and then it is being treated at the same location. And after treatment, which is a membrane bioreactor, and after disinfection, it is supplied back to homes through another pipe network, which is being used for toilet flushing, garden water. So they have tried to make the system self-sustained for 15 years.
There's stormwater harvesting.
There is no stormwater harvesting in this case. It is only the rainwater which is used for potable supply, and the treated wastewater for non-potable supply. Okay? So the garden all around over here is quite green because there is a water available for non-potable supply using the wastewater.
The entry is from that side. Means water is flowing through gravity to this.
So this slope is in this direction. It has a very good slope of 2-3 meters. So on that, so the depth of this pipe is only 1.5-2 meters. Here. And that's why you can see those tanks are partially above ground and in ground, underground. So I will show you in the next slide, they have on-site wastewater treatment for reuse and bore water supply for emergency purposes. What I'm going to show in this slide is, this is the rainfall. Sorry, this is the rainfall over here, and this is the demand. What you can see is, that is the continuous supply, which is available. But at this point over here, there was a shortage of water. So they operate under those conditions, that borehole which they have. So there are indicators available, the scale which can provide indication to the operator that now the water level in the tank has gone up to below certain level, and then he will run the pump, the borehole, tube well, and the water will be provided to them.
From that borehole, water will go to the storage tank or.
Yeah, storage tank. Yeah, because it is treated again. Yeah, it is treated again. I think I should have a few slides showing the treatment system. Not this one, but I will show you some of the other slides. So this is how this system is operating. It has the pressure pressure filter, UV treatment, chlorination. These are the for treating the rainwater. Okay. Pressure filter, UV and chlorination. For wastewater, we have membrane bioreactor, decentralized membrane bioreactors. Also, I have pictures to be sure. And then it is treated to the membrane bioreactor. It is collected into a raw, treated, recycled water tank, and then from there it falls back to. So the next part which I'm going to talk about is how to estimate the economics of scale. What should be the size? How many houses we can connect together through the system? So that analysis can be done for any system, like for recycle, wastewater, it can be done for rainwater, it can be done for collecting grey water from each and homes. So that analysis can be done. And how we have done it, I would like to show to you. The economics of scale calculation maybe there may be a number of applications, but the economics of scale is the term that is used to describe the reduction in cost per unit as more units are produced. Okay. So even for industry, if you are producing 1,000 or 20,000, maybe at some point you will see where the production cost will be minimum. Similar approach is being used over here. So what we did, we used how the life cycle cost will be calculated. All those equations are available. It's not nothing which is new. Net present value calculations, the capital cost of the infrastructure, recurring cost, all the data which you have to gather locally. Okay. So how much will be the cost of the construction of 5 kiloliter tank, 10, 20, 30, 50 kiloliter tank? Okay. The capacity of the tank can be calculated using the Ecocycle type of software or any software which you can develop by yourself, or even using that IS code. So basically the idea is that when you are comparing this type of system, you are looking the life cycle cost. That means conducting the analysis for 20, 30 years, looking the capital cost, looking the operation, maintenance, replacement of the part, and what manpower is required for operation maintenance for that period of time, and then you bring that cost to the net present value. Yeah. This is a simple engineering exercise which all you might have done in your projects, you might be doing for your PhD or your master. Very simple aspect of doing it. But there is a one chapter which is talking about all that analysis. Okay, you can look a little bit more in detail, and this I'm happy to share that complete report for this particular exercise. Yeah. And then we did the analysis for 50 years. We used discount rate factor of 7, but we also looked the uncertainty of sensitivity using the discount rate factor for between 3 and 11. So what we did is, I will use another the actual report, but you can see over here, we started with 4 homes. And I will go to the report and I will look at that report now. We started 4 homes in Central and Honolulu. Then we took 8 homes, then 16 homes, and then we started from that. And then you can see over here, this is the example of 24 homes. All the water has been collected centrally, and we designed the collection system, we designed the distribution network, distribution system, the pumping sites, the tank side, and estimated the cost of all that system, and estimated the life cycle cost over an analysis period of 50 years. Okay, so we took different sizes, and you can see the example for 24 homes and 96, and we did it up to, I think, 576 homes. From starting from 4 homes to 576 homes, because it was easier to start putting the homes. And then what we did, we estimated the cost, total cost of the system, and then what we did was, and this is another infrastructure which we costed for each and every option. In the option where there were 4 homes, I think the water could enter directly to the raw water tank. But as we increased the sizes of the number of homes, there was more depth of collection system, and then you need a suitable size of the sump well. Okay. And then you can have a submersible pump. Don't have to have a separate pump, but submersible pump that can be utilized for transferring water from sump well, and that pump will operate based on the level in sump well. You can have a sensors, and it will turn on and off based on that. And the similar function is being done in the actual case which I showed to you for 50 homes. Then you need to estimate how to calculate the size of the collection system for 50 homes, 10 homes, 30 homes, because your estimation of the size, the diameter of the tank size has to be based on how much is the flow which you are expecting, and that is the peak flow. And without estimating, with that estimation of its flow, you can't estimate the size of your pipeline, whether it is collection or distribution. Okay. So the estimation of that is also an important factor, and there is a lot of information which already been provided in that report and in the documentation how we have done it. So we collected some information and data based on some of the metering information which was available locally, and then we plotted it. As you can see, the peak flow rate is very, very high, and the numbers are very low. Why? Because if we are living in the house, if you see what is the pattern of your water, you will be using between 8 and 9. When you're going to the office, there is no demand the whole day. Then evening you're coming back and then they're using the water again. So there will be peaks. Peaks, only 2 peaks in the whole day. If there is no one living in the family or in the family, then maybe during the day there will be washing or some other activity, then that peak will change. That we call it diamond pattern. And that pattern, the peak will be high and for a single home. But as we start combining the houses, that peak flow will reduce on the water level. Because there will be uniform, there will be few not going to the offices, there will be few those staying at home, so the peak will reducing. So that's why you can see over here that the population is low, peak is quite high, but as we increase the number of occupants in the population, the peak factor is decreasing significantly. You can realize that.
More sample size, less variation.
More sample size, less variation. So in the larger cities, as the city is larger, the peak factor will be less. Even if it is in a distant town, the peak factor will be further reduced. Yeah. A lot of information is already given. But because this was the exercise for limited number of houses, and during a study there was a lot of monitoring was done for 10, 20, 50 homes. We tried to collect information from those studies, and as I indicated yesterday, there is a number of reports available in Urban Water Security Research Alliance, which I showed to you yesterday. There are reports available for which were conducted for monitoring the water requirement in different end-use monitoring. So there are a few reports available under that alliance, which will be very beneficial for you to understand how that analysis or how the monitoring is taken place. So we use that information and data, and we calculated the peak rates. And using those peak rates, we estimated using the ratio method how much flow will be from the roof and all those things, and calculating the size using manual equation for conveyance system. And then we use this UVQ or ecocycle for calculating the rainwater tank size using the daily rainfall data and also the daily demand data. Okay. We calculated for all those number of houses which we consider starting from 4 homes to 576 homes. The size of the rainwater tank was different, and I think you can see that.
How do you monitor? Is it if that fact is correct, peak flow rate is it stabilizes, so
Number of houses are high. Yeah.
or demand rate is different. So that's correct, but how do you monitor? Otherwise, supply level goes down unless until there's sensor or automatic system like in our campus. We have the similar system.
Yeah.
But the problem is that we don't have sensors. So
Yeah.
what they do, they just keep on opening the tank, उसका ढक्कन खोल के बार बार देखते रहते हैं उसमें कितने ज़्यादा है. Manually they operated, and the submersible is also there for gardening and other things. So the problem is that they just open it twice, morning and evening only.
Yeah.
And in between the supply level reduces or it becomes sometimes nil. So then we have to manually go and tell them. So how do you overcome these sorts of?
So basically, we have pressure sensors there.
So you need to
So
install.
pressure sensors can provide indication to the operator, and remotely they can check.
There must be, and then they operate automatically. Then supply is.
No, the pump is operated not automatically, but there is an indication to the operator that the water level has gone down to certain level.
Then operator.
Yeah. But it can be automated too.
It can be.
It is just a question of putting the infrastructure.
With the advancement technology, it can be.
Yeah.
But at least the sensors can be installed. Yes. this
Yes,
is right.
yeah. Pressure sensors, I think they're not that expensive. Yeah, you can install those pressure sensors and then it will provide information. By IoT is very common now. Remotely, you can have Internet of Systems that can provide information to the operator that there are issues with the water level now. He should be proactive in running the farm. Okay, so what we did, we looked at volumetric reliability, which we talked about, at a 94-95%, because 100% reliability, the tank size was quite large. And we are relying on the remaining amount of water to the end of the system, which can be either pipe water, which is coming from the municipality, or you can have your own tube well or bore water. So this is just to show you how you calculate this 94%. Because you can see over here, there is a sharp increase in the amount of water which is available by increasing the volume, the rainwater inside. But after that, there was less water available, and there was more increase in the tank capacity. That's why you can select a suitable range of rainwater tank size and more. So for example, at 90, you just need a tank size of 26.7 kiloliter. Okay. So you can very easily plot those tanks, that type of using those softwares. So we designed some well water treatment plant cooling and recirculation system using the local guidelines. And then pump size based on how much is the elevation where we have to pump, what will be the losses in the pipeline, all that we can calculate the pump capacity, which is quite simple mechanism. So what we found, and this is quite interesting to see, that for different size of the system, we plotted this curve. And this is the cost of the system per household. So for example, we designed first 4 homes system, and whatever was the cost we divided by 4, that gave us the cost per household. So as you can see over here, for a smaller system, the cost was very, very high. But as we start increasing the size of the system, the cost reduced. But after the second level, the cost starts increasing slightly. It can be because of topography. It can be because the overall cost, infrastructure cost, sizing. So what we found was that something between the minimum cost was for 192 homes or around 200 homes. But it was quite flat between 200 to 250 homes. That means if you are providing a system which is more than 190 and 95 homes, that is the economies of scale. That means you can design a system for so many houses in one system, and then if you are increasing the number, then you start thinking of another system. Then the numbers, if you have close to 190 and 150, then just for a few homes you are not going to reach another system. So this is just to show you how the economic scale numbers can be estimated. And there's a complete report of them, which I'm happy to share and give you a little bit more how each and every parameter for this. Then what we also did, we varied the discount rate factor, which we initially assumed 7, but we changed it from 3 to 11. And I think you can see over here, there is not much of a difference between that number, the minimum number of this. But it can be different based on the discount rate factor.
So in Australia, maybe the homes are made in a such a pattern so that these can be feasible. But in India, the homes are anywhere, not in a fixed pattern. How this can be feasible in India?
So you have to see the planning of that new development. And this is the pattern which we have used just to have the exercise. But you can use the pattern which is there and see how and where will be the suitable location for putting the common communal rainwater stuff. And then you estimate the overall cost. And then it will give you some idea for how many if communal rainwater can be suitable. So this is just this is not exactly the layout which is available. Okay. So you can see the one pattern which was over here, which is quite different. Okay. So this pattern is quite different what we considered. But for conducting any research or looking at a number, we assumed that this is the pattern. But what we can do is, what we can also see in this diagram over here, rather than putting the terminal rate into the center, if you have a slope, gravity is allowing you can have it at the end somewhere here, so you can reduce the cost of your collection system. So they get a number of options based on the local conditions. This is just one exercise to show you how you can do the calculate the probabilistic scale. What should be the optimal number to put a system? It is just a case system.
Deep break.
Sorry? Deep? Okay, we can break. Should we start? Are you finding it interesting?
Yes.
I think the best thing will be that try to explore the use of the software that will give you a little more interesting thing. It is like a game. Game. Yeah. That software basically.
You have to play it off.
Yeah, like we used to have computer games, it is on a similar pattern. So use it, run it. There is a very good manual attached to that, and there are some examples provided which will help you in case you have an issue with its application. Contact me, and I'm happy to provide you some help. But if you join 2 or 3 together and start using it, I don't think you will need anyone stuff. It is a software which can be used for planning urban development. It is not only for one thing. You can have as many points. You can have different clusters having different applications for end use. You can have different clusters for different demand, different configuration. So you can play all those together for a developed area of any size. It is just a question of how you're going to plan the whole area, and in that area, how you have designed or planned different set of houses. So it's very simple, and sometimes you have to mimic your situation. Means how you can get the required outcome with the help of models. So as I showed you before, that we changed the discount rate for estimating the life cycle cost. And even though we found that the outcome is very close to the what we use for 7% discount rate. This presentation includes only up to that point, but I will go to the report which we wrote. I will show you a few other aspects of what we did. In one case, we looked for that we don't have an achievement plan. What impact is going to have on the overall sizing of optimal sizing of the communal rate. So there is a lot of work that was done, and finally we published a research paper based on that. Now I'm happy to share that to give you a little bit more understanding, which I'm not able to cover everything. So overall, to finish this presentation and then coming to the another. So design of communal rainwater tanks on existing system and literature used. So we collected some information which was available in public domain and which was available. So you need some sort of a data for doing any life cycle costing, for identifying what should be flow, how much water will be collected, and I showed to you that peak flow curve, how we generated that curve. So there are reports available from where we collected that information to draw the diagram, which all those reports are available on the website which I talked to. So that there was an alliance between government of state government of Queensland. There were 3 universities and CSIR, which is similar to CSIR in India. So they all contributed some money, and there was teams from different organizations. They worked together on different aspects of different projects, and there are, I think, more than 30 or 40 reports which are available. They started, and they all are related to what? In climate change. There are a few reports in the climate change. And I think someone was talking to me about the downscaling of climate data yesterday. And you can also take the reports from downscaling from that website. But I have already shared one publication with you. Okay. And also, you were talking about the stormwater harvesting part. So there are a few reports about the stormwater quality and harvesting too. So there is a report which may be of use to everyone about the study which we conducted about the review of stormwater harvesting projects. There is a report available on that side, which has taken case studies not only from Australia, but there are a few case studies from outside. Okay, so all those reports are very useful. So optimal scale of 192 to 188 minimum cost occurred at 192 household for a flat topography. As the topography changes, those numbers can increase or decrease based on the way you plan for your system. Normally, the numbers can increase because the size of the collection system can be significantly reduced if there is a favorable topography. Capital cost influence the final cost, with 5 costs affecting 192 homes and beyond, and treatment unit costs below that. So, because there are two components, one is the cost of the pipe, the other one is the cost of the treatment units. So, up to a certain limit, it was more the pipe is dominating. In another case, it was more the cost of the treatment part was dominating. Sensitivity analysis of discount rate shows no change in the optimal housing number. So it is just based on the pattern of the cost of different units. The removal of treatment system does not affect the final cost significantly, because the operation and maintenance cost, there will be a change, but if you're looking for 50 years, time is spent, the overall impact will not be that high because it is one aspect of the overall network. Normally, the capital cost in infrastructure, the treatment unit is a smaller part of it. Okay, so what I will do now, I will go through the two documents. One is the book where providing you with more information. But today is the last session talking about rainwater. It will be changing to water sensitive design from DP. So I will discuss a little bit more. You can see how much material in detail is available in those documents. And there is a complete report on that Capital Monte example which I gave to you. We monitored the site over a year. We looked the water quality, we looked how much water is being used, what is the level of the water tanks, how much water was used through the alternative sources like the tube well or the bore water which we had. So we did complete analysis for a year. So that's important also. And those who are interested, they can download from their website. And also those who are interested in the wastewater side of it, there is a report on wastewater, decentralized wastewater systems. Over here, there was two developments which we monitored with different type of systems. One was bioretention, membrane bioretention system. Another was another filtration system and septic system. And there is a significant amount of information which can be useful for developing cluster of homes over here that can provide you about the suitability of different systems, the energy requirements for different types of systems, and also what is the level of treatment, and also how much greenhouse gas emissions are generated through different systems. So there is a report on the same website on wastewater treatment. Okay. One example is for the same development which we talked about, where we have not only the communal rainwater tank system, but we also have a wastewater which is locally treated and supplied back to us. So as you can see, there is a chapter number 2, which is dedicated to rainwater tank modeling. I have taken the one diagram from this report, from this chapter, which I showed to you, but it talks about different parameters which are needed they will play a significant role in the modeling. There are a number of models also available. There is a lot of information about the literature review, general concept in rainwater tank modeling. So those who are interested in conducting some research in this area, they can go through, it talks about all the losses and the estimation. So the author of this chapter, she developed a rainwater tank model just for rainwater tank. What I'm talking about is that software includes more than rainwater tank. It includes the overall integrated water management planning for the whole new or existing development. So please have the another important aspect in rainwater tank modeling is the impact of the time step in your estimations. You can do it on a monthly basis, you can do it on a yearly basis, as we saw yesterday in Professor Yadav's discussion and presentation. It was done on a yearly basis. You can also do the same analysis using monthly data. You can also do it on a daily data. And then you can also do it still on a 6-minute data or 5-minute data based on what data is available, especially the climate data. So those different time steps will give you slightly different outcomes. But as I said before, even the daily time step is good enough to get a proper outcome. So all that information is there. And also there is a talking about, if you see, this is a site I was talking about from where you can get the climate data for any location, but I'm not sure whether that will meet the requirement over here. Whether it is covering the geographical area, locally over here. But you can check the site and see how they have generated data, climate data for every location based on interpolating between the different rain gauges. And then the water demand data is another important aspect to take into consideration. And there are a number of end user studies which are the reports are available, which can also help in looking at the water demand data. Then there is a roof modeling, then tank water balance configurations. So as I talked about, you can have two situations. One, all your calculations are when the water has already estimated that it has entered into the rainwater tank, or your demand is before or after that water that has entered in the rainwater tank. So these are the two approaches, and there is a lot of discussion about both the approaches in this chapter. And then the spill rule, that how you're going to put the spill rule in your modeling. That the spill rule is that overflow from the tank. So all that information you can see the tank sizes, the reliability pattern, all this thing has been done. And also you will find some calculations based on the statistical approaches, like for example, if there are 1,000 rainwater tank systems, then, and they all are connected, then their sizes may not be the same, their demand pattern may not be same, then you can do some statistical analysis based on the ranges. So for example, your rainwater tank sizes are from 2.5 kiloliter to 10 kiloliter, and the demand may be similarly can be different. So you can do some statistical modeling to find
the overall pattern. So that is also being covered in this chapter, which is predicted annual water yield in Melbourne as a function of tank water size, connected roof area, annual demand of 150 kiloliter per year for toilet and garden watering. So all that calculations you can see. This is, I'm talking about the statistical analysis which has been done. So there is a lot of work which has gone into it, and I will request you that whenever you have time, go through it. So another aspect I talked about the impact of rainwater tanks in mains water saving. That analysis can be done by different means, and there are different approaches which has been covered in this based on the water billing in the area where we have rainwater tanks and the area where we don't have rainwater tanks. So you compare the water billing, and then you can see the changes in the demand in potable water supply because of that. So there are a lot of information that has been provided, and then there is a chapter on the economics of rainwater tank, that how to conduct that how much will be the cost per kiloliter. Yesterday, Professor Yadav showed the calculation that it was 7.7 rupees per kiloliter or something, or per liter, I've forgotten, but there was some number similar to that. Sorry?
7 paisa.
7 paisa.
For 50 years.
Yeah, on a 50-year basis. Okay. So 50 years is the life because of the concrete tank. But if you have other type of tank, then the analysis will be different because you are looking the life of the infrastructure. If it is a plastic tank, maybe life may be 10, 15 years. Your analysis will change. If it is a gravity system or a pumping system, then your full calculation, the cost of water will change. So there is a mechanism or methodology which is available, which can help you in conducting those analyses. Okay. So this is one thing and also we did the monitoring of 50 homes to understand, one is how much water is being used from the rainwater tank for different end uses, and then what was the water saving. So we monitored 50 homes, put meters in those 50 homes in each and every appliances. And then we did the analysis part. Again, that information is also very interesting to see how that was done by putting different meters and where we put those meters. Okay, so I will suggest, and there is one chapter on the social research, what community is feeling about those systems. So community consideration is very important to make the system successful. Sometimes the community is there and sometimes the community is not there. You're putting a new area, you're developing a new area. There is no input from the community. But what you can learn is by conducting the study in the areas where those type of systems already been implemented. So you can see there will be information about the questionnaires which were asked and the study that was conducted by a group of social researchers. This is just an outcome from those homes, 20 homes which we monitored, how much water is being used from the rainwater tanks, from the piped water supply. And so we plotted to see, basically why we did this study was that initially in the planning process by the government, they indicated that there will be a 40 kiloliter of water that can be consumed, that will be available from rainwater tanks per year. So, so you can see this average annual water consumption per household was 40 kiloliter. So there was a policy by the government, they made the rainwater tanks compulsory, mandatory, assuming that certain amount of water will be coming from rainwater tanks. Then it was essential to see that actually how much water is being utilized from rainwater tanks so that the policymakers can ensure that their policy is working. Because the overall regional planning was based on take into consideration that this is the amount of water that is coming from rainwater tanks. So that was part of the overall study to provide that information to the policymakers that this is what we are getting from those analysis. One was monitoring, actual monitoring. The another was comparing the different bills in different areas where there are meters, there is no meters. So different approaches you can see which were used for assessing that policy aspect. Because any policy that needs some monitoring, that once you implement it, what is the outcome? What actually, whether we are achieving that outcome or not. So until you go back to that area and see and monitor, monitoring is very expensive and time-consuming process. And normally, no one is very much interested in that part because of the cost constraint, because of the time. And if the results are not as per the desired outcome, no one will like to hear those outcomes. So there is a lot of work that already has gone into it, and this is the 80% of chapters in this book are based on the actual work that has been done under the same alliance. So you will see these chapters and also similarly detailed reports on that website. So the another aspect which I will cover rather than going through a little bit more in detail, which you can yourself can, one thing which we also looked that under that policy, they specified that how and where the rainwater tank should be connected and where the rainwater tank will supply. So, and then how much, whether the minimum roof area connected to the rainwater tank was as per the suggestions in the policy and the criteria specified in the policy. So we monitored nearly 200 homes to check whether the implementation was as per the specifications or not. So there is an outcome based on that too. So these are the things which you need to do to check any policy which is being implemented, mandate, and where the state is putting some resources or making it compulsory. Okay, so this is how we calculated the roof area, the gutters and everything, their numbers to check how much actually roof area is connected. So another report which I will show you. So this is the journal article based on the economic scale of a communal rainwater tanks, which we will share with you. But there is a whole report which has been written. So this is a complete report which will be of interest to you, and very detailed information has been provided, starting from how we have done the costing, the formulas, discount rate, the design, layout, what was the cost which we used for pipes, pumps, installations, concrete tanks, inspection, shaft and everything. So all that information is available. And based on that, as I showed to you, we started from 4 homes to 576 homes. As you can see, there are 4 homes over here. This is the configuration which we developed, and we went up to this. And another part which we looked was that it is not only looking the cost of the system, but we also looked if we change the slope, what is going to be the impact with the change in slope. That analysis is also being included in this report. So, and then the sensitivity analysis to see what changes are going to be there, and then the cost of different components, operation, pipes, maintenance, replacement, their contribution in the overall analysis. So all that information which can be of use to you, those who are interested in working in that space, or as Professor Yadav said, there is opportunities in future because of providing, and there is a lot of money the state is putting in. So you are not here only for one aspect, but in future you can be the part of all that development as a consultant, as an engineer, as a designer, as a service provider. So these reports can help you in if you are interested in future in consultancy or operation and maintenance of those systems. So this is one aspect, but we will be talking about other aspects in the evening about water system and design. So I will just open that manual for EcoCycle, and you will find that Melbourne climate data for, I think it is for 10 years. This is what we are also sharing with you. And this is the rainfall, and then maybe the evaporation and temperature. These may be the 3 data sets, and this data is available. You can use it for initially for running those software, or maybe you can just use for 1 or 2 years rather than 20 years or 15 years data which is available. And one thing what you can do is, based on this data set, you can see for each and every month you can sum that rainfall separately, and you can see the variation, monthly variation over time. You can write a simple software and that will give you the information every 30 days. You can plot diagram very easily, the distribution, monthly distribution very easily. Okay. So you can use this data to start with, and also I will just open this EcoCycle manual to show you. And also, although I have already showed to you, but there is a one file which I am sharing, which has a link. You can click it directly and then it will take you to that site. So this is also there available for you to use. I will just open this. So this is the manual which is available for EcoCycle, but there is a similar manual available for another software which is Urban Volume and Quality, UVQ. As I said, EcoCycle and UVQ, as far as the rainwater tank size and water balance part is the same, because same software is same engine has been used in both and the authors or the developers are the same. But only advantage in UVQ is that it has a contaminant balance too. Depending upon the type of water source you are using, it can also give you directly, but there is no kinetics involved in it. It is the user defined treatment percentage you have to define in that software. So in this software, you can see all that information, how this software can run. And there are examples, and some data is also, I think, provided by the author. And you can, so this is the this will be the first picture which you will be seeing on your screens when you will run it. And then you provide the climate data and all those daily, monthly, the right output, whether you need output on a daily, monthly, annual, and the monthly, annual outputs, whether in kiloliters and megaliters, and also the catchment size. Catchment size, if you're using your single home, then the size of the single home will be your catchment size. If you have 100 homes, then the then the area of the roads, parks, gardens will also be included in the overall catchment. Because that way you will like to know how much the stormwater is being generated by the whole catchment. Okay, so the catchment area is your whole development area. And that information will be provided over here. The number of clusters basically is that you have 20 homes of different allotment size, 100 homes of different allotment size. So that means you will have 2 clusters. Or you can have 10, 20, 15 clusters, as much as you can divide your overall development. So that number will go over here. So starting year of your analysis period, that means if you have a rainfall data for 20 years, then you can have from X year to Y year. Or you have single year data, then you can have single year. What it will do, it will also give you the average over the whole period, and it will also give the information individually for each and every year. Okay, so until you start working on it, I think you will not realize and then there is a different input occupancy rate, number of blocks in each and every cluster, all that information will go. So it will generate this diagram, this screen input based on your number of clusters. Over here, there were only 2 clusters. So then you can see only there are 2 input, 1 and 2 cluster, 1 and 2. If you have more, then it will automatically generate other clusters over here. And then it will give you the household waters demand and all those things. So you can simulate, and ultimately it will give you that sort of information for each and every cluster, which will have how much water is being used, how much stormwater is generated, how much wastewater is generated. All that information you can get from this software. And you can optimize your storages, which storage can be the rainwater storage, the storage can be the stormwater if you're using, or the wastewater system if you're using. So that can also give you the storage sizes. For each and every cluster, that information will be available. So I think I will stop it over here, and we'll see you in the afternoon. It's 2:30. Okay, we'll start another topic on water sensor and design. So this will be the end of the rainwater tank. Hope it added some value what Professor Yadav covered yesterday, and feel free to contact me or Dr. Sharma if you have any. If you need any help in future, but we'll share with you as many documents as possible for make you understand better. And if you are in a consultancy area, these reports will help you too. Okay, thank you very much for listening, and we'll see you